Hello everyone, welcome to this 12th lecture in the NPTEL course on Riemannian geometry. So last lecture we started this discussion of some basic constructions using the Riemannian metric, and we will continue with that discussion today. So let me just remind you of the couple of important points that we discussed in the previous lecture. So firstly, we discussed the construction of a local orthonormal frame for the tangent bundle. So this can be done on any coordinate neighborhood U. So as soon as you choose a coordinate neighborhood, one can take the standard basis for the tangent bundle on the coordinate neighborhood, namely del 1 up to del n, and then do a Gram-Schmidt process and end up with an orthonormal frame for the tangent bundle. Right, and then the second important construction that we discussed was this sort of musical isomorphisms. So we had these operators flat and sharp. So the flat operator takes in a vector field and spits out a one form. So in fact initially we defined this as a map that takes in a tangent vector and spits out a cotangent vector, but then we explained how this can be extended to a map, in fact a modular isomorphism from the set of vector fields to the set of one forms. So it takes in a vector field x and spits out this form whose components are given by g lower ij times xi, x upper I, right. So here, since you are lowering the index, this is called the flat isomorphism. On the other hand, the sharp isomorphism uses the inverse of the metric, and so alpha sharp is given by this expression, where the ith component of alpha sharp, upper ith component, is given by g upper ij times alpha j. And of course all throughout for the rest of the course we are going to use the so called Einstein summation convention, which means that you sum over all repeated indices. So here secretly we are actually summing over the j is repeating, so j from 1 to n. Similarly here secretly we are summing I going from 1 to n. Okay, so so this is what we saw in the previous lecture. So today I want to continue with some basic constructions. So the first construction is I want to describe the inner product on the cotangent space. Okay. So again let me give you a linear algebra aside. So V is an inner product space. Then we have this flat isomorphism from V to V star. So I have this inner product which I am denoting by these angled brackets on V. So using this inner product I can transfer, so using the isomorphism I can transfer the inner product to V star. So so given, let us say, f and g in V star, so we have this dual inner product of f and g is simply the inner product of, so you have this this operator, and then you have the inverse which is given by the sharp operator. So you simply define it to be this, right. So in other words, if you take the flat operator now with V star with this new inner product, then this is an isometry. right, artificially, because that is how we have defined the inner product on the dual. So with this definition of the inner product on the dual, this flat operator actually becomes an isometry, right? And similarly for the sharp operator, which is the inverse, that will also be obviously an isometry. Okay, so now we transport this entire thing back to a Riemannian manifold. So back to a Riemannian manifold. Okay, so so we obtain an inner product on the cotangent space at every point. Okay, so so my claim now is the following. So so recall that if x1 up to xn were coordinates, then we set Gij to be the inner product of del I del j, and this matrix G is symmetric positive definite. Okay. Now I can do the same for the dual basis on the cotangent bundle. So for the dual basis, so dx1 up to dxn we define G star upper ij. I am using upper indices because the dual basis vectors are represented with upper indices. So I just take the inner product of dxi and dxj and denote that by G star upper ij, and consider this matrix whose ijth components are given by the inner product of dxi dxj. So now my claim is that this is precisely G inverse. Okay, so strictly speaking, if you have to be pedantic, it's G is the transpose of G inverse, but you know G is a symmetric matrix, so its inverse is symmetric, so the transpose is the same as G inverse itself. So this is the claim. What is the proof? Okay, so so let's look at what is, so it's enough to show that this is the Kronecker delta symbol, right, because then that would imply that that this matrix G star is precisely the inverse of G, right, because this is the defining property of I mean this is equivalent to the statement that G star G is identity. Okay, all right. So so why is this true? Right. So what is right, so what is G star of ij? That's just the inner product of dxi with dxj. So that's by definition is the same as the inner product applied to dxi sharp and dxj sharp. Okay, but what is dxi sharp? Well, that's going to be given by the vector field g upper ik times del k. Similarly, dxj sharp is going to be given by gjl del l, right? So the inner product, that's going to be by bilinearity. I can pull out the metric components outside and you get the inner product of del k del l. So which is g ik times g jl times g jk. But now this represents matrix, the components of the matrix inverse, right? So here when you are summing over j, that's just going to give you a chronicle delta. So that's going to give you a chronicle delta lk, right, which in turn, sorry, this is kl, I copied it wrong, this should be kl, right. So this should be JL, and so now the repeated index is this L, right. So if you are summing over L, you should get the Kronecker delta, which is delta JK, right. So now when you sum over K, the only non-zero contribution is going to come when K is equal to J, so you are going to get Gij. So what we have shown is that the ijth component of G star is simply the ijth component of the inverse. Okay, so that proves our claim. So as a consequence, we have the following claim that that if alpha locally is given by this and beta is given by beta k dxk, then what is the inner product of alpha beta? What is the dual inner product of this? Well, this is just going to be alpha j beta k times the inner product of dxj dxk, which by what we have just seen is simply this. Okay, so we get this nice formula for the inner product on the dual. So the inner product of two forms. Okay. All right, let me make a quick remark. That suppose now you work in a local orthonormal frame. So suppose E1 up to En is a local orthonormal frame, and let us say epsilon 1 up to epsilon n is a dual frame. Okay, then we saw in the last lecture, at the end of last lecture, that epsilon I is precisely EI, you apply the flat operator to EI, right. So, or equivalently, that just means that EI is basically epsilon I and you apply the sharp operator to it, because flat and sharp are inverses of each other, right. But then by definition, if you take the dual inner product of these two, then that's going to be the inner product after you apply the sharp operator, which is the same as the inner product of EI EJ, but EI is an orthonormal frame, so this is of course going to be the Kronecker delta simple. So that means with respect to this inner product, this basis epsilon 1 to epsilon n is an orthonormal frame for the cotangent space. Okay. So then the advantage of using these orthonormal frames is that if alpha restricted to u is written in terms of this orthonormal frame, then the inner product becomes really simple. It just becomes a Euclidean inner product. So this is simply alpha k bk, where again Einstein's summation convention, you secretly sum over k, right. So the advantage of using these orthonormal frames is that the formula for the inner product becomes really simple. Alright, so now one can actually extend this to inner product on all tensors. Okay, in the following way. So let E1 up to En, and again it's easiest to describe in terms of these local orthonormal frames. On, let's say, some open set U, and let's take this to be the dual basis. Okay. So then if you consider this collection EI1 tensored EIA tensored with epsilon J1 tensored with epsilon JB over all possible choices for these indices, then this is a frame for the tensor products. So this is a frame for AB tensors, is a local frame for AB tensors. What does that mean? So this means the following two things. So remember, what was a tensor? A tensor was a multilinear product on a bunch of, on A copies of one forms, B copies of vector fields into smooth functions. So this means the following two things. Firstly, I need to tell you how this defines a local tensor. So it defines a local tensor in a simple way. So this acts on A covectors and B vectors, sorry, so it acts on A covectors and B vectors, and the answer is just you apply this component wise. So it will be E, so it will be omega 1 applied to EI1 multiplied by omega 2 applied to EI2, etc., omega A applied to EIA multiplied by epsilon J1 applied to V1, etc., epsilon JB applied to VB. So, so in this way, this collection actually defines an AB tensor over this open set U. And now one can check that for all AB tensors on M, the restriction can be written as a linear combination of this form. Okay. So, in that sense, this collection forms a local frame for tensors of the type AB. Okay. Now, in order to define inner product on tensors, I simply declare this frame as you vary over all possible choice of indices I1 to IA, J1 to JB as an orthonormal frame. Okay, so then one can check that this actually defines an inner product on all tensors. So, given two tensors of type AB on this open set U, we have the following simple formula to calculate the inner product. You simply multiply the corresponding components together. Okay, and then you sum over all possible choices of I1 to IA and all possible choices of J1 to JB. Each index I1 to IA can vary from 1 to n, each index J1 to JB can vary from 1 to n. Okay, so this is basically, I mean, if you think of a tensor as sort of a multidimensional matrix, you are essentially just multiplying each component together, right? As long as you are working in a local orthonormal frame for the tangent bundle and the dual frame for the cotangent bundle. So, one can also give a formula in terms of the metric components. So in terms of the standard frame, del 1 up to del n. So in terms of the standard frame for the tangent bundle, so that takes the form del IA, I1, I2, etc. up to del IA tensored with dx J1 tensored with dx JB. So in terms of this, if your tensor is given by these components, etc. up to dx JB, and your tensor S is given by S K1 up to Ka. Sorry, this should be I1 up to IA and L1 up to LB. Then we have the following formula, that this is given by simply multiplying these components, but then you will have to multiply by some metric components also. Times gi1 k gi1 k1 gi2 k2 etc. up to gi ka, and then corresponding to the lower indices, I have metric components with upper superscript. So you have g j1 l1 up to g upper jb lb, and again you sum over all possible choices of I1 to IA, K1 to KA, J1 to JB, L1 to LB. Okay, so you have this very scary looking formula, but you can notice what is happening, that corresponding to all these sort of upper indices, you think of them as the vector part of your tensor. Then you multiply by the corresponding metric components. That's how you compute inner products of vectors. The lower indices you should think as corresponding to the covector part of your tensor, and so then how do you compute inner products of covectors? You use G with the upper indices, you use the inverse of the metric, right? Okay, so that's as far as inner products of tensors go. The final construction that I want to talk about is that of a volume element or a volume form. Okay. So for this, let me remind you of something that one does in a smooth manifolds course. For at least this part, I am going to assume that M is oriented. Okay, so let me remind you of what being oriented means. That just means that there exists a cover U alpha by coordinate neighborhoods with coordinates that I will denote by x alpha 1 up to x alpha n, such that whenever two of these coordinate neighborhoods intersect, if you look at the corresponding Jacobian, that has positive determinant. Okay. So another equivalent way of formulating this is that there exists a top form, there exists an n form on the manifold which is nowhere vanishing, so that omega p is never 0 for all p in M. Okay, these are equivalent ways of saying that M is oriented, and then you call these the oriented coordinates, and the corresponding charts U alpha phi alpha as oriented charts. Okay. So why is orientation important? That comes from this fact and this construction, that very basic construction that one does, that if M is oriented, then one can actually define integration of top forms. Then one has the integration map so that takes in a top form and spits out a real number. So in general your M may not be compact, so you take compactly supported n forms. Right, and I won't go into the construction of this, but the idea is that you use sort of partitions of unity, and the reason why you need the manifold to be oriented is that at some point you have to check that the definition is sort of independent of the choice of coordinates, and so then you have to use this change of variables formula. And change of variables formula in multivariable calculus, if you remember, involves the absolute value of the determinant of the Jacobian, right? So you need these determinants of the Jacobians to be positive, so that you can throw away the absolute value and just have the determinant of the Jacobian. So then the definition of the integral makes sense. Okay, so I am not going into details, but hopefully you have seen this construction in a smooth manifolds course. So this is one of the main reasons to consider oriented manifolds. So now here's the proposition that we are interested in. So the point is that in high school calculus we learn that functions can be integrated, but once we take a course in smooth manifolds, we have to change our viewpoint and say that functions cannot be integrated, but top forms can be integrated, n forms can be integrated, right. So on the other hand, once you have a Riemannian metric, then it gives you a way to reconcile these two separate viewpoints. A viewpoint that you learn in multivariable calculus in high school or in your undergraduate program, and this more advanced viewpoint that you learn, that integrals are actually computed of n forms, not of functions, right. So to reconcile these two, one actually needs a Riemannian metric. So that is what the next proposition does. So let Mg be an oriented Riemannian manifold with oriented charts, oriented atlas, this collection of u alpha, phi alpha, and let us say coordinates x alpha 1 up to x alpha n on u alpha. So let d alpha 1 up to d alpha n be the standard frame with respect to the coordinates sorry, this looks like an infinity symbol. This is x alpha, okay, and let Gij upper alpha be the inner product of del I alpha with del j alpha, and similarly let G upper alpha be the corresponding matrix, okay. So these are all quantities we have seen before. So then my claim is that if you define this dVg, which is equal to d alpha on u alpha, where dV alpha is this form given by the square root of the determinant of G alpha times dx alpha 1 wedge etc. up to dx alpha n. So this is a local n form defined on this open set u alpha, but my claim is that if you put all of these together, then dVg is a global n form, okay. Or equivalently, what I am saying is that on the intersection dV alpha and dV beta agree. So then you get a global n form, okay. So this is just a simple sort of calculation. So let's quickly do the proof. So on the intersection, we have the following transformation formulae. So if you take G beta, then that is just going to be del x alpha by del x beta, this Jacobian transpose times G upper alpha times this Jacobian, right, because this is how a bilinear form, the matrix associated to a bilinear form transforms. If A is the change of basis matrix, then you have A transpose times the matrix of the bilinear form times A, right. So that's this transformation formula. So this implies that if you take the square root of the determinant of G beta, then the determinant of a product of matrices is the product of the determinants, and the determinant of the transpose is the same as the determinant of the matrix. So you are going to get the square root of the determinant of this Jacobian square times the determinant of G alpha. So whenever you pull something out of a square root, whenever you pull a square out of a square root, you get the absolute value of that number, but because we are working on an oriented manifold and with oriented charts, all of these numbers are actually positive, all of these determinants are positive. So if you pull this out of the square root, you are just going to get the determinant of this times this. Okay, so if you go back to our definition of dV alpha, the first part was we need to understand how this determinant term transforms. So we now understand that. The second part is how does this n form transform. Okay, all right. On the other hand, the one form, so suppose you write the basis of one forms as dx alpha as a row vector and the basis dx beta as the row vector dx beta 1 comma dx beta n, then these transform according to the rule that dx beta is basically dx alpha times the Jacobian given by del x beta by del x alpha. Okay, so now if you take the wedge product, the wedge product of this will be the determinant of this matrix times the wedge product involving the basis vectors here. So that will be the determinant of del x beta by del x alpha times dx alpha 1 etc. up to dx alpha n. Okay, so now you put all of these together. So what is dv beta? That's okay, but that's by our two transformation rules, that's going to be the determinant of del x alpha by del x beta times the determinant of del x beta by del x alpha times dv alpha. Okay, but on the other hand, these two matrices are inverses of each other. So these are inverses of each other. So which means that the product of the determinants is going to be 1. So that just means that dv beta is equal to dv alpha, and this n form glues up to give you a global n form. Okay, so now we can define, if f is a smooth function with compact support, we can simply define the integral of f on M to simply be the integral of f times dvg. So this is now a top form, an n form. So you know how to with compact support, so you know how to calculate its integral. So that is defined to be the integral of the function f. So this notion of integral depends on the metric. Okay. All right. So let me finish with the following sort of example and the notation. So the notation is that if you are working in dimension 2, we sometimes, instead of using dVA, we will call it dA, instead of saying dVg, we will say dAg. So we think of this as an area form, because for 2-dimensional things we typically reserve the use of the word volume for 3 and higher dimensions. In 2 dimensions we instead refer to that as the area, and hence this form is called the area form instead of the surface form, instead of the volume form. So let me just quickly maybe end with the following example. So suppose you have f is from omega is an open set in R2 to R, so it is a real valued function, and you look at the graph of the function. So this is the set of all xy f of xy sitting inside R3. Then we saw that the so let G be the restriction of the Euclidean metric to the graph. So corresponding to that we have the matrix, and we saw a few lectures back that matrix has the form 1 plus fx squared, fx fy, fx fy, and 1 plus fy squared. So now if you calculate the corresponding volume element, it is a simple calculation. You compute the determinant and take the square root, you basically get this formula. And if you have taken a course on multivariable calculus and done surface integrals, this should be very familiar to you, right? So by the way, I am working in dimension 2, so I should call this the area form instead of the volume form. So what is this? This is exactly the surface area element. On the surface of the graph, right? So when we learn surface integrals, we learn that in order to integrate functions on surfaces, you need to multiply by this factor, right? So this is essentially like the local scaling of the area when you are working on a possibly curved surface. And when we study this first encounter this in multivariable calculus, we sort of give a very heuristic but very non-rigorous argument to justify that this is the correct area element, right. So it turns out that to give the correct justification, you actually have to, I mean the only sort of rigorous justification is via volume elements of volume forms of Riemannian manifolds. Right. So this intuitive formula that one comes up with in multivariable calculus is actually the right formula, and that is because that is the Riemannian volume or Riemannian area form associated to the induced Riemannian metric. Alright, so maybe I will stop here. So in the next lecture we will introduce connections. So the point is, in order to do differential calculus, one needs to be able to differentiate vector fields, and it turns out that differentiating vector fields is quite a subtle thing on smooth manifolds. So that will bring us to the notion of connections. So that is what we'll start with from the next lecture, and then from there we'll move on to curvature and more sort of important concepts in Riemannian geometry. Alright, so for that's it for this lecture. Thank you for the attention, and I'll see you in the next lecture. Thanks.